20. Oh, we're on YouTube? Is that right? Lucky Google's working again for that. I didn't even know you could do that on here.
Was YouTube out everywhere, or was it just in the UK?
It was out here as well. So
it was Gmail, everything.
Wow.
Yeah.
Okay, guys, I've started the recording. I've started the stream on YouTube. In 1 minute, I will let the 35 people that are sitting in the waiting room in. If the student volunteer doesn't arrive, I'll just give you guys the 2 minute and 1 minute warnings for each of your sessions, both on your talk and on your Q&A portion. Does that work for y'all?
Yeah.
Okay, good deal. All right.
I was kind of joking with my partner this morning. I wonder if someone was like cleaning the servers at Google and just like tripped over the wire, just how much trouble that person probably got into. Okay, I guess people should be
almost set. Once I let everyone in, give them about a minute or two to connect.
Sure.
And I'll chat to you, David, through the chat when everyone's connected or most people are connected and you can start, okay? Okay, it's time. Are you all ready? Let's do this. Let's do this.
Ready me to introduce? Oh no, people are still coming in.
Let everyone get settled.
Hi to everyone coming in. We're just letting everyone connect. Give it a couple of minutes, let everybody get on. Okay, so welcome to our first track session during the MLSE 2020 conference. We're thrilled to be able to go ahead with this meeting. It's been difficult. We were of course hoping to have this in person over the earlier in the year. That didn't happen, but we're very excited that we've been able to make this happen at the end of the year or the same, even in this virtual world that we now live in. So thank you all for joining us. It should be an interesting meeting because of course there aren't too many meetings that really look at the application of machine learning in specific fields. And this particular track in astronomy is not a meeting I've attended before. So I'm personally very looking forward to hearing what all the talks. So today in this first session, we have 3 talks, each of them 20 minutes, and there'll be time at the end for questions. There'll be 5 minutes for questions. So I'm going to ask is at the end of the talks, or even towards the end of the talks, you can raise your hand on the participants list, and then we'll be able to, I'll come to you and say, you can ask your question, and you can unmute yourself and ask your question. Or if you prefer, you can just type it in the chat, either to me privately or just to everyone, and I can read out those questions, assuming that we have time to get through all the questions. So we should have 3 talks today. We're going to be starting with Daniel Tomeo, who is a Carl Sagan and Hubble Fellow at Princeton, and is going to be telling us about the long-term fates of planetary systems, in particular comparing feature engineering to deep learning. Then we'll be moving on at, let me get my timings right, at 11:30 to Emily Sanford, who recently left Columbia. We're sad to see her go, but happy to see her thriving at Cambridge. And we'll be talking about computational linguistics for exoplanetary systems. And then to close up the session to get your timings right, 11:55, we'll have Hugh Osborne, who's at MIT, and will be telling us about classifying and transiting exoplanets with deep learning. So that's what we have to look forward to today. I'm going to ask everybody to please make sure your microphones are muted during the sessions until, of course, we come to the end of the questions, and then when you're called upon, you can unmute yourself to ask your question. So with that, I'm just going to hold off for a minute just to make sure everybody has a chance to come on. And then we will switch over to Daniel and you can share your screen, get ready to go, and we'll get started soon. Okay, we can see your screen, but not the presentation. There we go. Just hold off for 1 second, and then I'll prompt you. Okay, I think we pretty much have everybody. We've just admitted the last people. So with that, we can get started. Daniel, you get 15 seconds extra, I guess. So Daniel, you can get started with your talk. I'll mute myself and leave it over to you.
Great. Well, thank you, David, and thanks to all the organizers for the opportunity to kick off this session. This is an effort we've been working on for a long time. We have some new results that I'm really excited about. But I wanted to start by maybe motivating why this question is interesting in the first place. So over the last 25 years, we found over 5,000 planets around other stars. And that journey has been full of surprises. We found a huge population in the region interior to where we have planets in our own solar system. There's widespread evidence for violent dynamical instabilities that have left survivors on very eccentric orbits. So a central challenge in the field really is understanding how these planets form and piecing together their sometimes complicated dynamical histories. Now, a fundamental problem in trying to do that is that while we have ideas of how planets form in disks of gas and dust, we typically find and observe exoplanets several billion up to 1 trillion orbital timescales later. And a lot can happen in that time. Nature generically seems to form systems that are dynamically chaotic. So these enormous timescales make it possible for even very weak chaos to drive instabilities at late times. So surprisingly enough, if you took our current solar system and you let it go for 1 trillion orbits, Mercury would almost certainly collide with either the Sun or Venus in that time. Okay, so that makes connecting models of planet formation to current observations extremely computationally intensive, and that severely limits the number of planet formation models that we can run. What these models typically look at is you start with a large number of smaller bodies, and their subsequent collisions and mergers leave you with progressively fewer, more massive planets. But if instead of brute force integration, you could quickly predict the time from one collision to the next, you could develop much faster formation models and explore parameter space in a more efficient way. Another important application is that because most of the exoplanets that we find them indirectly. Most of them have been discovered as they transit in front of their host star. So we get measurements of their size from how much starlight they block. We measure their orbital periods precisely, but we often don't have good information on their masses or eccentricities. So here's a real 3-planet system, Kepler 431, where we've taken the precisely measured orbital periods, but sampled a range of plausible masses and eccentricities which are unknown, and we've overplotted all those configurations. It turns out that when planets are close to one another like this, a large fraction of those combinations of masses and eccentricities are unphysical. They're just dynamically unstable. If you directly integrate each of these candidate configurations, you can strongly constrain the allowed parameters. In this case, to tighter levels than is possible with expensive follow-up observations. The problem is that some of these instabilities can take a long time to occur. So checking that they do not takes a long time, even for the few configurations that we've run here. And we have hundreds of systems more to analyze. So this is a big computational bottleneck where more efficient predictions would be very valuable. Okay, so here's the problem that we're trying to solve, which we'll first treat as a binary classification problem. We're given an input orbital configuration on the left, and our job is to predict whether that system is going to survive for 10 to the 9 orbits. We could have chosen different lengths of time here, okay, but 10 to the 9 orbits is a nice balance between being short enough that we can generate a large training set of configurations that we integrate directly to find out what the answer is, while still being long enough to be a reasonable fraction of systems' actual lifetimes. For reasons that I won't get into, the 2-planet problem has enough conserved quantities that you can solve it analytically. So the simplest case that might generalize to higher multiplicities and is unsolved is the 3-planet problem. So that's what we'll focus on. And to narrow down the parameter space for our training set, we drew all the parameters, masses, eccentricities, inclinations, separations from typical values observed in multi-planet systems. So we did a pilot study to see whether machine learning might be useful for this problem a few years ago now. And I think the most important result from that study was that we found that while making predictions from the initial configuration to late times is hard, one simple step that really improves the performance is to make predictions instead from short integrations. Okay, so we're trying to avoid doing this very costly 10 to the 9 orbit integration, but we can run a short one over 10,000 orbits in less than a fraction of a second. And there's lots of information from these short time series to extract that can help you make long-term predictions. So if you fast forward to last year, when we started working intensively on this again, we were having an internal debate on our team of what the best way forward is on this problem, whether we should be trying to use the parts of the dynamics that we understand to engineer meaningful features that could help a machine learning algorithm, or whether we should be using deep learning to allow the model to find its own optimized data-driven features. So we decided to pursue both. On the deep learning side, we had a really talented grad student at Princeton, Miles Cranmer, who along with Shirley Ho, who's speaking tomorrow, have a lot of experience with deep learning. Shirley also brought on Peter Battaglia, who's at Google DeepMind. So we really had an all-star team for deep learning. And we tried all sorts of models that perform well on this sort of time series data in other contexts. Tried all sorts of combinations of Gaussian processes, multi-layer perceptrons, CNNs, LSTMs. We even tried fancier 1D scattering transforms to try to encode the frequency information in these time series, but we just could not get anything to work and could not figure out why. But if we take a step back and think about the dynamics that we do understand, we can start to understand why. So this square represents a projection of our 20-dimensional training set. All our configurations have 3 planets, so we can always plot the period ratio between the inner planets on the x-axis, the outer planets on the y-axis. And the problems lie along these various highlighted lines, which occur at integer ratios between the orbital periods of a pair of planets. These are called mean motion resonances. And for these resonant configurations, the tiny tugs that the planets give to one another can actually phase up coherently to generate large effects, right? Like the wind on the Tacoma Narrows Bridge here. So if you plotted the instability times that we're trying to predict on this space, you would find that they vary fairly smoothly in the white regions far from resonances, but then spike by many orders of magnitude near each of these strong resonances. And that makes this problem a nightmare because no matter how you cut it, predicting instability times in this sharply punctuated space will require a huge number of parameters to capture all these sharp changes that occur across each of these lines. So we did two things. First, we generate our training set just from systems that are in or near these strong resonances. That lets us sample densely where the behavior is changing most sharply. So this plot is showing you our actual training set of about 100,000 three-planet configurations. And then this also provides a physically meaningful generalization test, right? If we're right that it's these resonances that are dominantly responsible for driving the instabilities in compact planetary systems, then our model that's trained only on systems near these lines should still generalize well to the white regions between strong resonances. We also used our domain knowledge to engineer features that partially encode these resonant dynamics and might help the machine learning classifier. So for example, for a single pair of planets who's dominated by one of these resonances, we can use perturbation theory to decompose their complicated eccentricity evolution plotted here on the top into a pair of much better behaved modes. So there's an analytic transformation from the top to the bottom where you can show that mode 1 drives the resonant dynamics and should have approximately constant amplitude, while the second mode should be approximately conserved. Okay, so transforming to this space makes it much easier to measure the resonant oscillation amplitude of mode 1. We simply measure the standard deviation across this time series and use that as one of our features. Another feature that we use is the amplitude of mode 2. Okay. In our idealized two-planet model, the amplitude of mode 2 would be exactly 0, right? So its deviation from 0 as a feature provides a measure of the importance of that additional third planet that's not in our model and of any non-resonant effects. So here's our model, which we call the Stability of Planetary Orbital Configurations Classifier, or SPOC. Here is our short 10,000 orbit integration, from which we measure 10 features, including the mode amplitudes that I showed you on the previous slide. And it's only after transforming to this much smoother 10-dimensional space that we train an XGBoost model, which is a gradient boosted decision tree classifier, to separate the stable from the unstable systems. And the end result is that we go from taking a stability evaluation that takes several hours through brute force integration to being able to do it in less than a second. So rather than show you how SPOC performs on our training set data, I'll show you how it generalizes to this real system that I showed you before, which is not near strong resonances, it's in the white regions. On the right are the stable configurations left over as determined by brute force integration. But so that you can see each configuration, we plotted a different way. For each evaluation, we're now just plotting 1 point for the middle planet's eccentricity vector. So this is a polar plot where the distance from the origin is the eccentricity, and the polar angle is the orientation of the orbit. We then pass those same configurations to SPOC, and 96% of the evaluations agree. And we go from needing a cluster to run this to being able to do it quickly on a laptop. Okay, so the crucial piece for the success of this model was our ability to use domain knowledge to transform from this sharply punctuated space to a much smoother one where prediction is easier. And that was successful despite our transformations being idealized and not perfect. But Miles realized that we could build that fact into a better network structure. And we decided to use it for the harder problem of not just binary classification into stable or unstable, but into actually predicting a time to instability. So here's our original time series of orbital elements like we had before. Right, so with Spock, we went, for example, from eccentricities in some of these green rows. And then we did an analytic transformation to transform variables in brown, which were these various modes, right? But now instead of using our analytic transformation to go from the green time series to the brown time series, we instead train a multi-layer perceptron F1 to learn a useful and possibly better transformation from our original space. The only pooling that we do in this whole process is to then take these transform time series that we've learned and take means and variances of each of those time series, just like we did with Spock. And then finally, we take that set of means and variances of the transform time series and feed that to a second MLP that spits out an instability time prediction. Now, I just want to say a few words about how we trained our model and how we built uncertainty estimates into it, starting with the fact that there is no area in astrophysics where it would be acceptable to take a set of data and, say, fit a line to it without giving errors on those estimated parameters, right? You couldn't possibly publish a paper where you take a set of data and say, well, our best estimate for the Hubble constant is 68, and then give no error bars whatsoever. But we do that all the time in machine learning. We fit all the parameters in our machine learning model to our training data by finding some minimum according to our particular objective function. And then we say, okay, that minimum, that set of parameters is my model. So you give me an orbital configuration and the black box says, yeah, that's going to live for 1 million orbits. Right, but how sure can you be that it wouldn't be 10 million orbits if you ran it, right? You have no idea. And that really isn't science, in my opinion. Now, we know that the right way to do this problem is to explore the region around the minimum using techniques like Markov chain Monte Carlo. If we're trying to fit a line to data, we then get posterior distributions for our two parameters, and we can measure their correlations. So that's the idea for Bayesian neural networks. Instead of having two parameters like for our line here, we now have thousands or millions of parameters for all the weights in our model. But we're still trying to fit this more complicated model to a set of training data. So there is no way to run MCMC for that many model parameters, but an approximate way that's developed by Maddox et al. In 2018 is to assume that the region around the minimum to leading order looks like a multidimensional Gaussian. So the procedure is to train your network the usual way, using backpropagation and stochastic gradient descent to take you to the minimum. But once you do that, you then turn up your learning rate, which causes you to do a random walk around this minimum, and you accumulate average values for your parameters along with a low rank covariance matrix. So this stochastic weight averaging gives you not only a more robust set of mean weights, but the fact that you're additionally fitting a Gaussian to that particular mode, that's the G in SWAG, gives you information of what the region around that minimum looks like. Okay. And then multi-SWAG is doing that same process, but doing it several times. So the parameter posterior is always multimodal. So fitting a couple dozen modes will then give you a more robust estimate of what your model uncertainties actually are. Okay, so the end result is that instead of having a single best fit set of neural network parameters theta, we have a posterior distribution for theta. And that means that instead of outputting a single instability time, we can repeatedly sample from our posterior of network parameters to build up a distribution of estimated instability times. So let me close by showing you how that works in practice on the strictest generalization test that we did. we took a set of 17,500 numerical integrations by Alberto Sidel in 2017, which fixed the separations between adjacent planets to be equal and only varied that single separation parameter. So that corresponds to configurations along this diagonal black line where the period ratios are equal, and it includes both resonant and non-resonant systems in between. Additionally, they took the 18 additional parameters that are not visible in this projection, and they fixed it to a single value. So all eccentricities are set to 0, inclinations are 0, all masses are set to the same value of the mass of the Earth. So this really corresponds to a 1D cut through our 20-dimensional training set where we really have no examples. And even worse, these integrations have 5 planets instead of 3 planets. So all our training is done on 3-planet systems, and now we're trying to predict on 5-planet systems. So this is what we get. The numerical result is in red. It's in red. It's in black from direct integrations. Our median prediction is in blue, along with our 1 sigma uncertainties in lighter shading. We can faithfully match those results, including the sharp dips that occur at various resonances as you're crossing them, as you sweep through parameter space. And then all of this, despite the fact that this test is at one extreme limit of our training set data and using nearly double the number of planets. Okay, so we're very excited about these models. We're already working on applications. We're using them to constrain parameters in real exoplanet systems. And in cases where those parameters are already known observationally, we can also look at how close those planets are to the instability limit as a new constraint on the planet formation process. I think a central lesson from this exercise is that we're not obsolete, that scientific applications, often we have, maybe incomplete, but we have knowledge that's useful, both in generating features that can be useful or in structuring our networks in ways that help the algorithm learn. And finally, that we really should be moving towards probabilistic models that provide uncertainties, and that there are approximate methods for being able to do that. Okay, so I'll stop there and happy to take questions. Thank you.
Thank you very much, Daniel. Yeah, we have time for questions. I can see one straight away in the chat from Ashley. If you'd like to ask a question, please raise your hand at this point. I'm going to read out Ashley's question. How sensitive is this to the choice of learning rate, and how large of a region in latent space did you explore?
Yeah, I mean, all of this is experimentation, right? You try one learning rate, it doesn't work at all, and you have to tune that down. We tried to take as much of the manual tuning out of it as possible, and sort of use a package like HyperOpt to explore the hyperparameters that we used in a optimal way, whatever that means. So I don't think I can give you a very good answer specifically to that question, but that is something that we definitely had to vary, like you typically do in any problem like this. This was in reference to error bar estimates.
Yeah. Maybe I'll ask a question.
Oh, sorry. You're asking how much do you have to turn up the learning rate to then walk around the minimum? I can't give you an exact number there. I think it will depend on your applications, but I think that the best place to look would be those 2 papers that I cited. There's Maddox et al. In 2018, and then Ismailov and Gordon Wilson in 2020 for multi-swag. Yeah, look up those 2 algorithms.
Yeah, Daniel, I'd like to ask about the tails of these distributions. Obviously, it's great that your uncertainties, the Gaussian assumption seems pretty good for getting the median, and the 1 sigma seems to be agreeing well with your numerical results. Sometimes one might be interested in the tails of the distribution if one wanted to say, 99% confidence that the timescale is less than some number, like a one-tailed p-value or something. So how well does this swag or multi-swag work for the tails? Have you looked into that?
Yeah, I mean, I think no matter what, the tails are always going to be the hardest thing to get right. And, you're definitely doing this in an approximate way, right? You have so many parameters that you can't do this rigorously. So I would think that the tails are the first thing that you get wrong. I can't give you quantitative estimates for what we get in the tails. We did take the uncertainties, right? We can take our predictions with uncertainties and compare how far away each of those predictions were from the real values. And the agreement really does look like a Gaussian, but we haven't quantified exactly how big the errors are in the tails. I think that's a good question.
Okay, we're just about out of time. I want to advertise if we can continue discussing on the link wova.com. There's like a board there where people can continue to discuss anything that comes up from today's session, and you can see the link. It's just in the chat there to go ahead and join. Okay, so with that, we're going to thank Daniel one more time and then move on to Emily. Okay, so if you stop your screen share, and then I'm going to let Emily screen share and I'll introduce her while she's getting up. So Emily Sanford is, as I said, a recently graduated student from Columbia, and she's now starting as a research fellow at Keyes College at Cambridge University. And we'll be telling everybody about a project that actually was born from the DSI. So with that, I'll let you take it away, Emily.
Great, thank you, David. Yes, as David said, I moved on to Cambridge University, but I'm going to be telling you about a project that was done in collaboration with David and also Michael Collins from the Computer Science Department at Columbia. And this is a project about applying a very new technique from natural language processing to the problem of understanding exoplanetary systems. So I will begin by just showing you a view of what exoplanet systems look like as we understand them today. So this is a view of the Kepler orrery. These are all of the exoplanet systems discovered by NASA's Kepler Space Telescope between 2009 and 2013. We know of something like 4,300 exoplanets organized in 3,300 exoplanetary systems. And here you see them all overlaid on the solar system. So they don't tend to resemble the solar system. We're quite limited by our observational biases to discovering planets that are close into their stars. But nevertheless, they do sort of resemble each other. And there's clearly an underlying logic governing the types of planetary systems that we are discovering and that exist in the universe. I want to draw an analogy here between this population of exoplanetary systems that we're just beginning to understand and discover, and a body of untranslated text in a language that we don't speak. So I've chosen this snippet of Esperanto Wikipedia. I think we have all a common enough linguistic basis to sort of be able to understand that there is a structure and a meaning governing the construction of these sentences, even if we don't understand what that structure is or what they say. And I think there are actually a handful of quite specific analogies we can draw between linguistic applications and astronomical applications when it comes to this question of how do we translate or understand a body of untranslated text. The first of these is an approach called part-of-speech tagging, which was developed in linguistic applications for organizing words by the functions that they play in their sentences. So this is identifying words that serve as verbs versus nouns versus adjectives. In astronomy, and particularly in exoplanet science, we're interested in an analogous question of whether planets fall into natural categories in their systems, and if so, what those categories are, and how many there are, and whether we can find them. Another potential analogy you could draw here, in linguistics, people are interested in the question of predicting next or missing words in an incomplete sentence. We're all familiar with this from autocomplete or text prediction in our smartphones. As astronomers, we're interested in predicting often the next or missing planet in a sequence or a planetary system. We know that our knowledge of planetary systems is incomplete. There will certainly be planets that we're missing because of our own observational limitations. And it would be great if we could identify where those planets are likely to be, if we could narrow our search space, and hopefully find those planets more efficiently moving forward into the future. Finally, an ultimate goal of linguistics when faced with a body of untranslated text might be to deduce what were the grammar rules that generated this text in the first place. And we can draw an analogy to trying to understand the rules that created planetary systems in the first place when we're looking at just the outcome of those processes billions of years later. So what we see is a population of exoplanetary systems that all formed according to some rules, underwent billions of years of evolution, and now we're seeing the results, but we would like to understand the origins. And so each of these three areas is one where we have a lot to learn from linguistics, in my opinion. But for the rest of the talk, I'll be focusing on this first one, part of speech tagging and its implications for exoplanets. I want to begin by explaining what part of speech tagging is and why it's useful before I move on to how it's done. I've chosen here as an example text, just another snippet from Wikipedia. I'm going to take this snippet and strip away all the formatting, all of the capitalization and hyperlinks and punctuation, leaving only the words. And I've labeled these words by their quite simple part of speech labels. There are definitely more nuanced or sophisticated part of speech labels you could apply to English text, but these are just the absolute basics. And so why is this useful? Why is part of speech tagging done at all? The first reason is that having labeled these words, I can actually take the words away, leaving only the part of speech labels. And you can see now that certain patterns become clear that were obscured by the individual choices of words in the original snippet. So now you can see that certain sequences recur frequently. You see often the snippet or the sequence article noun, you see pronoun verb. Other sequences don't occur at all. You never see two conjunctions in a row, for example. And these patterns were not clear before because they were sort of obscured by the individual choices of words in that particular Wikipedia article. Whereas these patterns would exist regardless of the article I had chosen. So in that sense, part of speech labels don't model the quote unquote noise of the individual content in any particular snippet of text. Another reason part of speech tagging is useful, and this is a particular new advance in part of speech tagging, it's only been possible in the past couple of years, is that you can do it in an unsupervised way. And what I mean by that is that you can train a model to label parts of speech in a large body of text without providing that model first with a library of millions of correctly labeled training examples. The reason that that's possible is, I can show you, if I replace these part of speech labels by slightly more abstract labels, you can see that the patterns that I alluded to before still exist here. You still see the sequence black square, blue square happens often, red square, yellow square happens often. It doesn't actually matter what those labels mean. The computer doesn't need to know that a gray square represents a conjunction in order to pick up the patterns in which conjunctions cooperate. And so this is really useful for us as astronomers looking at exoplanet systems, because if there are natural categories that planets fall into, analogous to parts of speech, we certainly don't know what those are in advance, and we don't have a library, I wish we did, of millions of correctly labeled training planets. We have to sort of go in from a place of total ignorance. So that's why part of speech tagging is useful and why we're interested in applying it to planetary systems. Let's move on to how it happens. So let's imagine that we're interested in tagging the third word in this sequence is, or the third planet in this planetary system. We're going to call that our target word or our target planet. And then the rest of the planetary system or the rest of the sentence will be our context. And remember, what we're interested in figuring out is what is the correct part of speech label of the word is, or of that target planet. What is the category it belongs to? So it's important to recognize that there's actually two independent streams of information about that thing that we're interested in finding out in these sequences. The first is in the target itself. If I handed you the word is, you'd be able to tell me, oh yes, that's a verb. If I handed you a medium-sized terrestrial planet, you'd be able to tell me, oh yes, that's a medium-sized terrestrial planet. But if I didn't give you that, and instead I gave you the surrounding context, if I gave you a sequence, a raven, blank, a bird, or if I gave you a sequence that went sun like star, small terrestrial, medium terrestrial, blank, medium terrestrial, Jupiter, you might, based on your knowledge of the solar system, be able to guess that what's filling in that gap is a medium-sized terrestrial planet, or at least not a Jupiter. So the context contains information about the target's label, and so does the target. In order to do part of speech tagging, and this is the recent sort of theoretical advances that enabled this project, you exploit those two streams of information independently. So you have your target data, you have your context data. For our purposes, we're looking at our target data is the radius and period of the target planet. The context data is the radius and period of all the neighbor planets, plus the effective temperature and surface gravity of the host star. And you train two neural networks. One of them sees the context data, the other sees the target data. Each of them outputs a prediction of what the correct part of speech label or category label is for that target. And so the goal of these two models is to agree as far as possible. This is our loss function. In more technical language, we're maximizing the mutual information between the prediction of the context network and the prediction of the target network. And this has been shown to be very successful in inducing part of speech labels in linguistic applications. This is the first application to astronomy. So let's move on to some results. I want to show you first the data set that we're working with. This is specifically planetary systems, again, that were discovered by Kepler. Overall, there's 4,300 planets. For the rest of the talk, I'll only be talking about our test set. So we took those 4,300 planets, split 70%, we trained on 70% of them. I'm showing you the results of the remaining 30%, which the model did not see initially. So that consists of roughly 1,300 planets. This is what they look like in radius versus period space. Daniel showed a version of this plot already. And so again, on the y-axis is planet size, and on the x-axis is planet period, or how long it takes the planet to complete a full orbit around its star. I've marked the position of Earth on this plot. You'll notice that Earth is quite alone. That is a function of Kepler's observational biases. We're heavily biased towards finding planets that are closer in and larger than Earth is. If we look at the host stars that these planetary systems are orbiting around, this is what they look like. On the x-axis here, we have stellar temperature. From hot on the left to cold on the right for sort of historical astronomical reasons. That axis is backwards. And similarly, the y-axis is surface gravity, which is a measure of how puffed up the star is, essentially. So at the top, we have giant stars, which have very low surface gravity. On the bottom, we have dwarf stars, which have high surface gravity. They're much more compact. And the sun is marked there as a yellow circle smack dab in the middle of that distribution. And so the question is, what parts of speech or groupings do our networks find among these planets and stars? There's a slight complication here, which I have to elaborate on a bit. A free parameter of our models is how many clusters or how many groupings we ask them to find among the planets and stars. We can tell the networks to go looking for two classes or 6 classes or 10 classes, and they will obligingly find them. But we want to pick up on physically meaningful categories or physically meaningful classes, which means that we have to be sure that these classes are somewhat independent of the hyperparameters of any particular run of the model. So I'm about to show you, just scrolling through, the class boundaries that the networks draw for varying choices of the numbers of classes we tell them to find. This is when we ask the networks to find 2 classes. On the left, we have the class boundaries drawn by the target network, which once again sees the radius and period of the target planet directly. So it draws its class boundaries in the planet plane. The right 2 panels are the boundaries drawn by the context network, which again does not see directly the properties of the target planet. It sees all the surrounding contextual information. So actually, it's drawing its boundaries most definitively in the stellar plane, because that's essentially the most direct information about the system that it has. Although there is also weak information in the planetary plane. So I'm going to step up through increasing numbers of classes that the networks are asked to find. You'll see that the class boundaries get ever more complicated. This is a little bit of a problem because you can imagine increasing the number of classes the networks are told to find arbitrarily. And eventually, if it matched the number of data points in the set, we'd get essentially a perfect fit to the data. We have to be able to penalize the number of the complexity of the model in some meaningful way. Not obvious how to do that analytically. Ideally, you would define some analog of the Bayesian evidence. But in the absence of a sort of rigorous mathematical way to do that, what we can do instead is just ask, which of these classifications or classification boundaries seem to be meaningful and which seem to be sort of arbitrarily switching around as a function of how many classes we tell the networks to find. one way to do that is just to ask which of the points in these planes are never subdivided from each other, regardless of how we mess around with the networks. And there's a handful of sort of big groupings that are never subdivided. The ultra short period planets always get stuck together. The long period small planets always get stuck together. And then as we look at sort of ever smaller groups of planets that are never subdivided, what we find is that there are sort of ever contested regions of this space. The open circles in these plots represent planets or stars that are continually shifting allegiances as we mess with the model. But there are also these regions of parameter space that don't tend to be subdivided, and they tend to clump together. And so if we merge all of the contiguous clumps together, what we find is that we can identify these sort of stable regions of the plane that don't tend to shift their allegiance if we mess with the model. In the planet plane, what these groupings represent are our parts of speech by our linguistic analogy. And in the stellar plane, these are groupings of stars or systems that tend to behave similarly. So if I just label these by what their host stars are like, we have the giant stars tend to host systems that all resemble each other, the warm dwarf stars, the cool dwarf stars, and then this strange group that I've marked in yellow that's sort of overlapping all of the other dwarf stars. Turns out these are the host of compact multi-planet systems. So the network picked these up as a group that all behaves the same and shouldn't be subdivided from each other. By our linguistic analogy, these are different types of sentences, basically, these types of planetary systems. So I just want to briefly show you what each of these types of systems looks like in slightly more detail. This is system grammar, if you will. This might be a bit rushed, because I know that I don't have infinite time. I'll begin with the cool dwarf systems. So these are the systems that are highlighted in blue on this plot. I do want to note these are not all of the cool dwarf stars in our sample are, quote, cool dwarf systems. These are only the ones that belong to the cool dwarf cluster that was picked up by the context network. So if we look at what these cool dwarf systems looks like, each system is plotted as one row in these panels on the right, and then all of the planets belonging to cool dwarf systems are plotted here in this panel on the upper left. If we compare that to all of the planets in the test set, we see that certain types of planets are over or underrepresented in the cool dwarf systems. So in particular, the long period small planets are overrepresented, as are the short period giants. The long period giants are underrepresented. And another interesting feature of these cool dwarf systems is that they're almost all single planet systems. So actually a more appropriate name for these systems would probably be low multiplicity cool dwarf systems. There's only two planet systems and no systems of higher multiplicity. If we look at the warm dwarf systems, which are the ones in green on this plot, we find very similar trends, although slightly weaker. So here we have the planets in the warm dwarf systems. We find that exactly the same groups are over and underrepresented as in the cool dwarf systems. And we find that, again, multi-planet systems are underrepresented, although not as strongly as in the cool dwarf systems. We also find that just in terms of period ratio between neighboring pairs of planets, these systems tend to have, are on average the most compact of any grouping. Moving on, the giant systems are actually the easiest to interpret of all of these. Planets and giant systems are overwhelmingly lonely long period giants. This is very straightforwardly a function of the observational biases of Kepler and of the transit method in general. It's very difficult to see a small planet around a giant star. It's much easier to see a giant planet around a giant star. And so you preferentially pick up giant planets around giant stars. So correspondingly, the giants are overrepresented. All the small planets are underrepresented. And again, these planets tend to be lonely. They're almost all single planet systems around giant stars. The compact multi-planet systems, I think, are the most interesting group. This is a group that's defined not by any intrinsic property of the host star, but rather by the architecture of the system itself. So the network is learning here from the planet context and not from the stellar context. If we look at these compact multi-planet systems, they are definitely the most homogeneous group. They consist exclusively of small short period planets, which are strongly overrepresented, and there are no planets from the long period or giant groups. And you can see in the architecture plots on the right how homogeneous these groups indeed are. There are no single planet systems in this group, and this group has the highest average multiplicity. Finally, there are a handful of stars, well, not a handful, there are a large number of stars left over that don't belong to any of these groupings. These are the ones plotted as open circles in this plot. These are the ones I'm calling indeterminate systems. And these are really eclectic. These are all of the systems that are left over that don't fit neatly into any of the other categories. I think the most important thing to take away from this talk maybe is that all of these systems, including some of the most individually interesting systems, all of the 5 planet systems and the 6 planet systems in our test set, very few of those, though there are, belong to the indeterminate group. I think it's pretty clear that these are just the systems that we don't know what to do with yet, and the systems that don't constitute any big grouping of their own yet, because we just don't know of that many planetary systems. The planets that are over and underrepresented in this group, in support of this view of these are just the ones that are left over, are exactly the complement of the ones that are over underrepresented in the dwarf stars. So if a group is overrepresented around the dwarfs, it's underrepresented here, and vice versa. These are just the planets that are left over. And overall, multi-planet systems are strongly overrepresented in this group. So multi-planet systems in general just don't tend to fall into neatly the other categories. So to conclude, I think we can say that planetary systems are not random overall. They are structured like language. And these new tools from linguistics can show great promise in helping us to decode the grammatical patterns in these systems. And systems do tend to fall into clusters, although our understanding of these clusters is definitely incomplete. The low multiplicity systems around cool dwarf stars, the systems around warm dwarf stars, systems around giant stars, and the compact multi-planet systems seem to behave differently from the population overall. Thanks very much.
Thank you, Emily. We have time for questions. Please raise your hand or put it in the chat.
I don't think I have a way of raising my hand, but I would like to ask a question.
Yeah, sure, go ahead.
I was curious if, in addition to your model learning about the grammar of planetary formation, whether you think that it's also mixed in with learning something about the observational biases that we have, and if there's any hope of teasing those apart somehow, or if you thought about that.
I mean, definitely, you can see it most cleanly in the giant systems. I mean, I think we can't say definitively that giant stars don't host smaller planets in addition to these giant planets that we do see, right? One way to perhaps start to think about detangling those, and this has been proposed by some of my colleagues here in Cambridge, would be to apply this method to planetary population synthesis data sets, where you have a very clean idea of the underlying ground truth and see what you get. But given that sort of the output of simulations like that are their own can of worms that I don't have my own expertise in, I've been hesitant to do that myself. So I think that would be the neatest way, because you could control for observational bias and the underlying truth quite carefully.
Ashley in the chat has asked a question which is related. She says, I know that NLP propagates societal biases. Is there any analogous issue that you have seen in your work? Like some systems only seem to cluster in the context of the biased Kepler mission beyond just under/over-representation of some systems?
Yeah, I mean, I will say again about the giant systems, I think it's very unlikely that this is a full view of the planetary systems around giant stars. And I mean, also, there are huge swaths of parameter space that we just have a very poor idea of the planet occurrence rates at this point. Particularly from the transit method, we don't really know anything about long period planets. We've only just begun to sort of discover systems that could generously be called analogous to the solar system. And so, yeah, I mean, I think you would have to be quite careful in sort of extrapolating these conclusions to differently biased data sets. Although it would be interesting, I mean, like one sort of regret is the wrong word, but it is slightly annoying that we can't include the true hot Jupiters in and among these data sets, just because the biases of the methods that discovered the hot Jupiters are different from the transit method biases, right? So I think extrapolating to other data sets is difficult. And I think it would be, without a sort of homogeneously observationally biased sample, you'd have to be very careful about the conclusions you drew from this.
And Ashley has a follow-up question on this, asking that language has logical inconsistencies. Do you know how NLP methods deal with this? And if there is some cool way to use this for exoplanet systems?
I don't know a ton about the underlying NLP applications. The major advance that this work is based on is a new technique, this dual neural network technique, maximal mutual information. It's the first unsupervised method that's been competitively accurate as supervised methods for part of speech tagging. But as to what are the underlying limitations of that accuracy in the linguistic space, I don't know very well. I mean, there are certainly complications that arise because the parts of speech of many words are very ambiguous. I think one analogy you might draw to exoplanets is that I think it's unlikely, given that planets are sort of continuous in their properties in a way that words are not. Defining clean, non-overlapping classes is probably a fool's errand in some way. There will be a continuum of planets that have sort of probabilities of membership in different classes, but sort of talking of planets as falling into discrete categories at all might be a mistake. So that is actually one of the limitations of the analogy to linguistics. But I guess that sort of doubly complicates the inaccuracies of part of speech tagging in the first place.
Well, I think we should thank Emily again and move on to our next speaker. So thank you, Emily. Okay, so our final speaker for the session is Dr. Hugh Osborne, who is joining us from MIT and is going to be telling us about classifying exoplanets in a slightly different way, not with NLP, but with deep learning.
Yeah, that's right. Can you hear me okay?
Yeah. Go ahead, Hugh. I'm going to mute myself and let you take over.
Great. Yeah, so I'm going to be talking a little bit about how me and my colleagues listed at the bottom have been using deep learning to try and classify transiting exoplanet candidates. And luckily, I've had two talks ahead of me to kind of set up the world of exoplanets, so I don't have to go into too much detail there. But I thought I'd start by just kind of outlining the problem which we kind of try to get together and add a deep learning twist to, which is basically going from raw data to planets. So what typically happens in TESS and Kepler as well, which we've heard about from Emily, is that you start with a lot of raw images that come down. In fact, we get a video. In the case of Kepler, we have a video of a part of the sky for 4 years, something like 80,000 data points or 80,000 frames in that video. But it tends to be that you don't kind of care about the whole image. You care about small regions of it. So we typically cut out what we call postage stamp or a target pixel file around the stars that we want to observe, and that becomes our input video effectively. And you could argue that maybe you want to start here and start doing deep learning from the pixel level, but it makes a lot more sense, in my opinion, to kind of progress a bit and to turn that video into a one-dimensional light curve. So this is brightness over time, and it is in these light curves that we typically find planets, although there are a lot of other things going on here, so things like jumps and bumps in the light curve because of things the telescope is doing. But we have a relatively good way of removing those using aperture photometry and then systematic correction. So then this is kind of what we end up with. This is simulated test data, but you can see in here that you have wiggles from stellar variation, you have dips just from cosmic rays and other things going on the detector, and you have dips from other things as well, astrophysical objects in there, some of which are planets, but the majority of which actually aren't. The majority are false positives from eclipsing binaries, so it's two stars passing in front of each other. So what tends to happen now is there's a transiting planet search that happens called TPS in Kepler and TESS, and these search for threshold crossing events, which are basically planet candidates. And this tends to be done in phase space. So rather than searching for individual transits in the light curve, which can tend to look pretty washed out because have your low signal to noise, planets are strictly periodic. So you search in period space, you add up all of the transits in a certain period, and at once at the period of the planet, you get a really nice strong signal where originally you didn't have a signal. And this is the signal of the planet passing in front of its star once per year, effectively. And this phase folded light curve at the bottom, and the binned light curve here in terms of the purple points, that's quite important to keep note of, because that's the highest kind of signal to noise data we have of the planet transit. And that typically tends to be where machine learning can try and go in there and classify. So this is what you kind of what you might see. These are candidate signals now of the test simulated data we had. But as I said before, the majority of these aren't planets. The majority of these are either eclipsing binaries or just noise from the telescope. And the minority of these are kind of planetary signals. So what tends to happen then is we do data validation, which in the case of Kepler and TESS is like fitting a model to the data and telling us something about the planet parameters, if it is indeed a planet. And then there's a human classification step where humans look at the output of this data validation and the light curve, and they classify it as, is it a binary, is it stellar activity, or is it the planets we're after? And then eventually those candidates get observed from the ground, and they either get confirmed or statistically validated and end up in the exoplanet catalogs. But it's this stage here, this human classification stage, which is kind of the heavy, the most difficult bit to do in some ways, and it's certainly the most time consuming. I have vetted many exoplanet light curves, and it's fun to find the planets, but the majority of time you're not doing that. You're looking at junk. So in Kepler, this was done on all the quarters, all the data from 150,000 stars, 4 years, as I said. And then in TESS, we do this every month. There's about 20 of us, and something like 200 hours we put in to vet and find the planets in that data. So, I mean, the question is really, can a machine do this process better? And the answer has kind of been yes since 5 years ago. So this was one of the first attempts by the Kepler team. They used a random forest, McAuliffe et al., and taking the data validation steps, so the model fit to the light curve and other kind of statistics generated from the light curve, they used 230 features and used that as their inputs to random forest, with 3 outputs, 3 classes, and they got something like 94% precision and 97% average precision on based on the human labeled kind of data labels they had at the start. And then 3 years later, there was the first major application of convolutional neural networks to this effort. So that was AstroNet, which was written by Chris Chalou and Andrew Vanderberg, and they use deep convolutional neural networks in order to basically try and classify from the light curve alone whether the Kepler candidates were planets or not. So these use 2 inputs, both of which had multiple convolution layers. So the one input was the full phase folded light curve, so the whole period. You can see here the transit, and then this is in fact a secondary eclipse in the middle. And this was inputted, and there were 10 convolutional layers, and then there was a zoom into the transit as well, which had 4 convolutional layers, because this transit is obviously the most important thing to look at in terms of classification. And then 4 fully connected kind of classical convolution neural networks, sorry, and then the output at the end. So this was kind of the standard. They did a pretty good job. They did a better job than the Astro or than the random forest that came before. And this has been built on, including this is what we built our models on, and this has been built on in other ways. So there was Datillo et al. In 2019, and also last year as well, there was application to TESS vetting for the first time, which also included a zoom in on that secondary eclipse if there was one. And this is actually currently in use at TESS, where we do the vetting at MIT for TESS candidates. But I should talk about what we did. So this is actually a couple of years ago. We got together at this NASA Frontier Development Lab. So this was a NASA meeting to try and bring machine learning experts and astronomy and space science experts together to create something to advance the field of space sciences in some way. And so this was our 4-person team, and Megan was the lead of the Kepler kind of program, and I was leading on the TESS data side. So in terms of Kepler, we were using the same input data effectively as Chalou and Vanderberg, 16,000 candidates from the Kepler DR24, which had labels from humans, and about a quarter of these were planets, with the majority false positives. And we processed this data to get rid of anything that we know that isn't going to be helpful. So getting rid of stellar variability and phase folding onto the period that has been found by the transit planning search, and then binning these to global and local views. So and so we did something similar for the tests input data as well. So we had 4 simulated sectors. At that point, there wasn't any test data to work with. So this was actually different because it wasn't vetted by humans. It was simulated, so we knew the exact ground truth. We knew exactly what we injected in. And these were put through the test pipeline from the pixel level, in fact. And we ended up with a similar number of candidates, but slightly fewer planets, so only about 14%. The majority of the signals being these like junk systematic data from the light curve itself. And we processed the data in a similar way. So, I mean, probably this is basic to everyone watching, but just some simple definitions. So true positive is where you predict a planet in this case, and it is in fact a planet. False positive is obviously when you predict a planet, but it's not. And false negative is where you have a planet that you predict is something else. And so in terms of precision, which is also sometimes confusingly known as accuracy in the machine learning world, but not in the science world, you have the true positives divided by all of the things that are predicted to be a planet or predicted to be the class. And then recall is kind of the inverse, where you have all of the things that are in fact a planet in this case as the numerator, and the denominator being the true positives again. And then what you can do is, because you don't get a Boolean output, you get a number, a prediction between 1 and 0 as to how close, or how as to your classification. So you end up plotting a PR curve, a precision recall curve, and this is basically a threshold between 0 and 1, where you can tinker with that threshold and see as a function of that threshold how likely you are to classify it. So basically, precision recall curves up to the top right, that's good, and a precision recall curve that kind of goes straight across the middle, that's bad. And then, sorry, in multi-class models especially, you want some way of giving a score for the whole model. So what we tended to use, and this was an average precision, which is basically a weighted average for the precision of all of the classes. And it can also be thought of functionally similarly to the AUC class. And so basically it's the probability that a random positive sample is correctly predicted at any threshold or any place on the PR curve, effectively. So one of the things we did to improve on Chris Chalou and Andrew Vandenberg's method is we were trying to use domain knowledge. So basically take what we know of the sample of planets and of false positives, and put that into a network, turn that into a way that we can include that to better classify. So in this case, we noticed that, well, I mean, one of the key ways of identifying false positives in exoplanet transit surveys is to use the centroid. So this is the position of the center of light over time. And this moves effectively when the source that is producing the eclipse isn't the source you think it is. It's a source like still in the pixel, but around the different fainter background star. So you can see on the bottom here, these two curves at the bottom show this clear centroid shift, which if you didn't include this, you might think this dip was a planet, but it is not. So rather than using a 1D input, as Chris Chalou and Andrew Vandenberg did, we kind of used the same thing, but we did a 2D input, so, or well, 1D, but 2-layer input, where one layer is the light curve and the next layer is the centroid. But we copied the same convolutional and fully connected layers there. So another thing we used stellar properties. So as we heard a little bit there from Emily, that the stellar properties actually determine what planets you can find. And inversely, if you have a certain star, you know that you can't find planet around it, and therefore you know immediately for a giant star, for example, you wouldn't have a small planet. You're far more likely to have a star. So this can be important. So we included this into the fully connected layer alongside the convoluted information from the light curves in order to try and encapsulate this information and convince the model to use it. And the cool thing is that it works. So this blue line here in terms of the PR curve is the Chris Chalou's model, and the orange line where we include both stellar information and centroids is obviously a lot higher and higher in average precision, higher in precision recall for the same threshold. And actually, it's the stellar information that helps most in this case. But both of the stellar information and the centroids curve are contributing here. Another thing that we did, and there's lots of little tricks that you can do in order to improve your model, and one of them is data augmentation. So basically, you can modify your input data to create new samples for the neural network to look at, and this helps prevent overfitting and helps train the model a lot better. So so you can see on the right here, we take that input transit and we can transform it in certain ways to produce different light curves. And the main way to do this, and the most useful way, is to take the noise we have, and rather than just take the average flux in a certain bin, is to use the computed error we have for that flux bin and use that to sample a normal distribution for each point, therefore creating different flux levels within that bin, but on average producing the same effect. And another thing you can do is, because transits are symmetrical, you can just mirror it in the x direction around the center of transit. And because often the transit center is not perfectly aligned, you can shift a little bit in x and in terms of in the x direction here, and it just but all of these effects basically increase the number of samples and help train the model. And as you can see here, once again, we get an improvement of about 3 or 4% from data augmentation. And another little trick you can do is assembling and cross-validation. So what you normally see with machine learning is you have all of your samples and you split it into a training and a validation and test step. But it's actually a lot better if you can split your training samples into, say, k different sections, and you use each of those sections once to validate a different model, which is being trained on the other n minus k parts of your data. So this means you get multiple trained models, and this also means that once you have multiple trained models, you can ensemble, it's called bagging as well, over all of those models to give an average of the output classification. But I think you should always have this test set, even if you do cross-validation, apparently. So in terms of Kepler, we ended up outperforming ExoNet, as I showed earlier. So we ended up with a average precision of about 98%, which is more than 3% larger, or no, 2.5% higher than AstroNet. And this is actually the best classifier of the Kepler candidates that has yet been applied. Although there's still 2% to be gained here, so I'm sure someone will come along and beat that in the future. And also, one interesting thing is that we do much better at lower signal to noise, which is probably because we have this extra information from the star and from the centroids, which is able to which where you have low signal to noise, you obviously have the least information in your light curve, but the information coming from the star and the centroid is kind of can be the same. So this really helps here. When it comes to test data, we changed the model a little bit, and we reduced the number of bins that we put in from 2000 to 1000, simply because, well, typically test planets are on shorter periods, so you don't mind so much about a shorter bin size, and that actually increases your signal to noise per bin, so your signal to noise in the transit itself is higher. And because we had a ground truth where we had it simulated data, we could use multi-class modeling. So rather than just planet, not planet, we were using EB, blended eclipsing binary, planet, and junk signal. So the result here, well, one other thing you can do with multi-class modeling is you can do balanced batch sampling, because if you have a misbalance like we have here, where the junk signals outnumber all of the other classes, by balancing the classes for each kind of small chunk of samples you put into your model, this actually helps train and helps equalize effectively the training for each of the classes you have, rather than simply just guessing the majority class each time, which can happen without balanced sampling. So in terms of tests, our performance was not quite as good as Kepler. So we were only getting about 96% average precision in the 3-class model, which was the best model. There wasn't much difference between just using a binary planet, non-planet model and using 3 and 4-class models, although yeah, I'll come back to that. So in terms of the three-class model, we were doing kind of best on EBs and unknowns, and not so good on planets in terms of how many we were recovering, with a lot of junk signals that were predicted as planets that weren't. And as a function of signal to noise, it's also interesting to see we have slightly worse than Kepler, but then TESS is a lower signal to noise machine, so maybe this is one of the reasons. One of the interesting things is the junk signal, so the kind of systematic noise remains high, and this suggests maybe that the model is learning the systematic features in the data set, which is actually really interesting, because unlike a transit model, we don't have a way of parameterizing the systematic transit-like features we find. So this is actually a useful thing, and suggests that maybe this is the most useful thing. If you can learn everything that's not a transit, then you can throw out everything that looks like a junk signal, and you're left with only things that are astronomically real. So transits and EBs. So this is kind of promising. One of the reasons, actually, so when you compare the average precision that we get from Kepler and TESS, one of the, we asked ourselves what the question was. And one of the reasons is actually that in Kepler, there's human vetting, whereas we had simulated ground truth, which meant that there were actually things that we put into the data set which wouldn't have been identified by human vetters as planets, even though they were in fact planets. And this included things like monotransits, which our data would basically see one transit and try and flag a multiple transits there. And even though there is a transit in the data, and our model is seeing a transit and seeing a planet, it doesn't match the period that the planet actually has in reality, and so it gets thrown out as not being the label effectively becomes junk, even though it's found the planet. And so actually, if you look at all the false positives, something like 65% of those are either from monotransits or from period confusion. So if you include these near misses in, where it finds a planet that is a planet but it finds the wrong period, then you increase the planet precision from 90 to 95%, which kind of matches closer to what we found on Kepler. So one thing, once we had this model trained on simulated Kepler or simulated test data, we can apply it to real test data. And this is obviously far faster than 200 hours per sector for current test people. So this took about an hour to pre-process all the light curves, and then about 5 minutes to predict. But I mean, real data and simulated data aren't the same, so there's different noise in there, and maybe the injections don't match what we actually find in reality, and we don't actually have a ground truth to compare with. So when we applied it to the real test candidates, we only recalled about 60%, 61% of the what the test team said were planets, and we were missing about 39%. About 9% of those we thought were EBs, but 30% we thought were noise, just kind of junk signals. So there's obviously something going on here. And I think probably the reason is that we trained our model to identify junk signals in simulated data, and those signals aren't the same in real data. So that's obviously something that we have to retrain our model on real data. And we were able to predict something like more than 100 new candidates. But actually, when I went looking through these candidates, many of these are actually binaries around giant stars, or they share the same period and epoch, which are signs of being false positives, but false positives that we didn't inject into the simulated data we have. So this is kind of the problem here, is that if your simulations don't match reality, then anything that doesn't match is going to sneak through the cracks and be misidentified when you apply that model to a different data set, basically. So in conclusion, by using domain knowledge, you can get a more accurate classification of transiting planet candidate vetting. And so far, Kepler ExoNet is the best performing model we've seen on Kepler, with something like 97.5% precision. TESS ExoNet performs well as well, getting up to 95% precision on a simulated training set, but it doesn't do so well on real data yet. And we have a few new candidates, despite many of them not looking great on after manual vetting. we have a few candidates which are being followed up still, so we may well have found some planets that were missed here. Yeah, so with that, thanks very much, and I'll take questions.
Thank you. We do have a bit of time for questions. Technically, we have till 12:30, so we have time. If the raise hand feature isn't working, then as I just put in the chat, you can just type, I have a question. Okay, Emily has a question. Okay.
Yeah, great talk, you. On the previous slide or 2 slides ago, you said reflections from bright binaries were causing some of these false positives. Could you just explain what that means?
Yeah, so one thing that one check they have in the Kepler pipeline is they basically take all of the periods and epochs they have from all of the signals, and they cross match them. And sometimes what you'll have is the same period and epoch of like 10 signals all found with the same period, and all of those 10 signals are immediately thrown out, because what that is a sign that there's something that's contaminating multiple stars that is causing the same signal to be on all of these stars. So that could be reflections from binary, that could be a binary that's made its way accidentally into the calibration data or something like this. So in the case where we're just throwing light curve, centroid, and stellar parameters into a model, we don't get a chance to do this test. So, or at least we didn't put it in as the domain knowledge. So we have no way, or the model has no way of telling if periods match. So this is one of the downsides, but I guess it's one thing we could just put into the model at the ANN stage. So at the fully connected layer stage, like we put in the stellar parameters, we could put in, okay, how many other signals have a matching period, and when this is high, it should throw out the data. So this was more just an oversight in terms of how we built the model. But yeah, this is there's a lot of things like this in the real data that you don't have in the simulated data. So it's very hard to teach a model to do that.
Yeah, I think video crosstalk is another way that can happen as well, between pixels. Max Hipperson has his hand raised. Max, do you want to unmute yourself and ask your question? You're still muted, Max, if you're trying to.
Hey, there we go. Sorry, I couldn't unmute myself there for a moment. I was just wondering what matters more in like catching transits? Does it like flagging false positives more of a problem than missing potential positives? Just because like the accuracy and recall and precision don't really include any information on the true negative cases.
Yeah, it's a really interesting question. I mean, I think it determines what you want to use the planets for. If you're trying to do occurrence rates and you want a model where you can get a really good sample of, you can basically catch all of you get a really high precision sample, so everything in your sample is real, then obviously you tune it to have high accuracy, and you wouldn't care so much about recall. But in terms of how we usually do this vetting step is we're actually quite conservative in terms of we just want all of the planets to get through, and then the people on the ground with telescopes can find out like if they're real or not. So we would be more, if I go back to so we would be more keen to have a high recall in order to that we catch all of the planets, and so we can use follow-up observations to make sure that the ones we do catch are real. So it really depends what you're going to be using the sample for. But in terms of filling in this step, we would want a high recall, and so we would kind of prioritize catching as many planets as possible. Maybe at the downside being we would have false positives in the list.
Still time for questions. I'm going to ask one to Hugh. I wonder how you deal with, or how it performs for planets which, to connect to Daniel's talk a little bit, which interact and have very large movements in their times of transit. So then you don't get that nice, clean period folding effect, transit timing variations. And so how does the algorithm perform if there's a very large wobble?
Yeah, so that's something in Kepler that is a problem for some of the multi-planet systems. When you have these transit timing variations where one planet is interacting with another planet, effectively what happens over the entire mission, if you're trying to phase fold, is you smear out the data and you end up taking a nice U-shaped planet signal and turning it into a V-shaped signal, which looks more like a binary. So we didn't do anything special to try and account for that. Basically, we just took the period that came out of Kepler and used that as the true period, and didn't incorporate the fact that that might be changing orbit to orbit because of a companion. I'm not sure anyone's looked at the outputs and see if any of these TTV planets have been misclassified. But that's an interesting question, that one we should check. Yeah.
Any other final questions? Okay, if not, I guess we're gonna let everybody go get some lunch before we continue this afternoon, as we'll be moving on in the next session. So there'll also be a panel where our speakers will be there available for questions as well. We'll be talking about the limits of machine learning that Melissa Ness will be sharing. So I encourage everybody to come back for that. So thank you, everybody, and thank again to our speakers. Wonderful job. If you have any other burning questions, please do go to the wover.com board. I can already see there's a few questions in there. I've been putting a few in myself. And we'll see you this afternoon. Okay, bye, everybody.